In section 8.6, which is called numerical integration, we're going to go back and look at areas under curves, but instead of using rectangles to estimate areas under curves, we're going to use trapezoids. Notice in this section, the homework problems, they say do them with trapezoidal rule and do them with Simpson's rule. We're not going to do Simpson's rule, so just use trapezoidal rule. Okay, so what is a trapezoid? A trapezoid is a quadrilateral, four-sided figure with two of the sides are parallel. So if we call, you call the parallel sides the bases, whether they're vertical or horizontal, doesn't matter. So if I call this B1 and the length of that side B2 and the height of the trapezoid H, which is what you would expect to do, the area of the trapezoid is the average of the bases times the height. In other words, B1 plus B2 over 2, so the average of the bases times the height. So that's the formula for the area of the trapezoid. Now, why do I need this? Well, when we were doing areas under curves before in Calculus 1, we chopped it up, the graph, we chopped up the interval into equal pieces, even though they didn't have to be equal, and we drew rectangles. And we found the area of each rectangle and added them up. Well, if I'm going to do the same thing with trapezoids, you're going to chop up the interval, draw trapezoids over each interval, and then take the area of the trapezoid. So that's why we need the area here. Okay, so let's start setting that up to see what that would look like. So I'm just going to draw a generic curve. Okay, so suppose we have this curve, and I'm going from A to B. No problem. Okay, so let's chop this interval up into n equal pieces. Okay, so remember we found delta x, which was b minus a over n. Right? Okay, so if we chop this up into equal pieces, so we call we call a x naught, and we're going to call b x sub n. Just like you did before when we did rectangles. And so we chop this up into equal pieces, okay? So this width is delta x, and then you're at x sub 1. And then move over another delta x, and this is x sub 2. Right? And you keep going. The last x value is x sub n, so the one right before is x sub n minus 1, and that width is delta x. So we chop this up into n equal pieces. We're using an equal partition, so each width is delta x. Keep going, delta x. Okay, now, remember when we did rectangles, initially, we were consistent. We took all the left endpoints or all the right endpoints, and we used one set or the other to figure out the heights of the rectangles. Well, here we're doing a trapezoid. So what we're going to do is for every x value, we're going to go up until we hit the graph. So x naught, we're already hitting the graph. xn, we're already hitting the graph, right? No problem. So all the others, just go up and draw a vertical line until you hit the graph. So, it's terrible, but okay. So I hit the graph there. I hit the graph here. You do it all of points in between, and at xn minus 1, I go up and hit the graph. Now remember, we're not trying to draw a rectangle. You see the issue, like here. If we were doing rectangles, do you make the height of the rectangle here with this point, or do you make it here with this point? That was either right endpoints or left endpoints. But here we're drawing a trapezoid. Now notice here the parallel sides are the vertical lines. So the trapezoid I'm using here, it's turned on its side, okay? So B1 and B2 are my vertical lines here. Well, to make a trapezoid, what we're going to do is just connect the two. For the first interval, we have these 2 points. Just connect them. And then for these 2 points, connect them with a line segment. And then these 2 points, connect them with a line segment. So if you do that, we have a trapezoid, trapezoid. Okay? So we're using both endpoints to connect to make a trapezoid. When we did rectangles, use the left or the right. Here we have to use both. Okay, well, just to get ourselves going here, what's the area of the first trapezoid here? So I'm talking about determined by the first interval. Now again, be careful, right? The bases that I've drawn here, the parallel sides are the vertical lines. So what do? We take the average of the bases, so 1/2 what? Well, the base here, the two parallel lines are the vertical ones. How far is it from here to here? Well, it's the y value at x naught, isn't it? This is the point x naught, f of x naught, if I call this f of x. Right? So the height of the rectangle is f of x naught. Just like, sorry, the length of this side of the base is f of x naught, just like when we did heights of rectangles. So it's the average of the heights of the parallel sides. So that's f of x naught. And then what's the length of this line segment? It's the height, right? The y value at x1. This point is x1 f of x1, so the length of that side is f of x1 plus f of x1. And now we have to multiply by the height, but what's the height of the trapezoid? Right? Well, what's the distance between the parallel sides? So the h here is the delta x. So that's the area of the first trapezoid. So here's the base, you take the average of the bases times the height. Okay, well, what does the area of the second trapezoid look like? So again, it's going to be an average of the bases times the height. So it's going to have the same flavor here. So the average of the two bases and then times the height, okay? Well, the height's going to be that distance again, right? Right, the height of the trapezoid is the distance between the two parallel sides. That's delta x again. Now, what are the two bases in the second trapezoid? Well, it's the height of that side, of that, and the height of that. But notice that's f of x1. And notice that distance is f of x2. Okay? So you would continue this. Area of that trapezoid, area of the trapezoid, area of that trapezoid. Let's see. I don't need my picture anymore. Let's see if we can write a formula for the sum of the area of all n trapezoids. Well, it's the area of the first one, 1/2 f of x naught plus f of x1 delta x plus, well, the area of the second one, 1/2 f of x1 plus f of x2 delta x plus dot dot dot. Oh, I guess I shouldn't have erased my picture. We didn't do the area of the last one. But what's the area of the last trapezoid? Well, it's 1/2 the average of the bases, and then the height's going to be delta x again. That's no problem. Now, in that very last trapezoid, right, the two bases were the heights of those line segments at xn minus 1 and xn. So it's going to be f of xn minus 1 plus f of xn. So whatever interval you're working on, it's just f of that, the left endpoint, and f of the right endpoint. Okay. Let's see if we can clean this up a little bit. Notice every single term has a half and a delta x, half and delta x, half and delta x. So we can factor that out front, half delta x. And notice we have f of x naught plus. Now we have, so I've factored out the 1/2 delta x, so now I'm just adding up all the f's. I have an f of x1 here and an f of x1 here, so that's 2f of x1. Okay, I have an f of x2 here, but the x2 is going to show up in the next term as well. So you're going to have an f of x2 plus another f of x2, so 2f of x2. And when you keep going, let's look at the last one. Right. Well, let's look at the f of x1 again. Notice when I have f of x1 as the first term of the sum, realize there's an f of x1 as the second term of the one right before. And here, f of x1 was the second term, so the next one, f of x2, is going to be the first term. So where's f of xn minus 1? Well, that's the first term here, so be aware it's going to show up in the term right before. So we're going to have dot 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 2f of xn minus 1s. Again, when you think about that picture, right, here was xn, here was xn minus 1. So when you do this interval, you count xn minus 1, and when you do this interval, you're going to count xn minus 1. Okay, so it shows up twice. Now what about xn, right? F of xn only shows up once. because when you draw the picture, f of x n, you only use that line once. So it's plus f of x n. So f of x naught only shows up once, f of x n only shows up once, but all the points in between has a coefficient of 2. Okay. Now, just to match the theorem there, we could replace delta x. Remember, the formula for delta x is b minus a over n. Okay. So this is the formula for the area of the trapezoids. Now realize the area of the trapezoids is not going to be equal to the area under the curve, just like the area of the rectangles is not equal to the area under the curve. But the area under the curve, I don't need this anymore. The area under the curve should be approximated by the areas of the trapezoids. So the trapezoidal rule says the area under the curve is approximately equal to that. Okay? So this is the area of the trapezoids. If n is large, you would expect the area of the trapezoids to be close to the area of the curve. So that's what it says in theorem 8.3, the trapezoidal rule for approximating the integral, right? So the area, the integral, which if your curve is not negative, right, then that is the area of the curve. The integral is approximated by the area of the trapezoids. So that's the first. So we proved the first part. Okay. So then it says in the theorem, moreover, as n goes to infinity, this approaches the definite integral. Remember, the definite integral, the definition was the limit of a Riemann sum, and we did that with rectangles, no problem. When we took the limit as n went to infinity of the area of the rectangles, we got a definite integral, okay? That's how we know that, the definite integral was the area of the curve. Okay, so let's do some algebra on this. Now, I hope you have your notes in front of you, because I'm not going to write every step down. I'm just going to explain how they're getting from one step to the next. Okay, so I'm not going to write limit yet. I'll just do it at the end. So let me rewrite this. Well, let me just write the whole thing again. So we had 1/2 delta x, f of x naught, plus 2f of x1, plus 2f of x2, plus plus 2f of xn minus 1, plus f of xn. So that's the expression I have right here. So that is the area, again, if the curve is above the on or above the x-axis. That's the area of the trapezoids. So, okay, so I'm not worried about the limit yet, but I'm down at the bottom of the page here. Now what they've done here, look at the difference between that very first step, which is what I have here, except for the limit sign, and the next step. What they've done here is right here, all they've done, I'm going to write in blue what they've done differently. What they did is they put plus f of xn minus f of xn. So that's what they did going from the first step to the second step. Notice that's 0. So all they've done is add 0 to that. So it doesn't change the value, it just changed the appearance. So that's all they did there. And then in the next step, what they did, okay, so I'm on the third line here, is they've distributed that 1/2 delta x all the way through. Okay, so if you do that, you get 1/2 delta x f of x naught plus, now the half times the 2 is 1. So you just get f of x1 delta x, half of the 2 there's 1, plus f of x2 delta x plus dot dot dot, half of the 2 is 1, f of xn, n minus 1, minus 1, delta x. Now notice here, there's 2 f of xn's. So now it looks like these. Multiply that by the half delta x, you get plus f of xn delta x, because there's 2 of those now. And then we still have this term here, but times 1/2 delta x, that's minus 1/2 delta x f of xn. Now, hopefully now you see why they did this adding in and subtracting. Why would they do that, adding a 0? Because they wanted the 2f of xn to match all the ones before. All the other ones, besides the first term, these all had a 2 in front. They added an f of xn and subtracted 1 out, so you could get a 2f of xn there, and now this looks just like all those. That's why they did that. Okay, so that's where that step comes from. And now what they do in the next step, okay, again, just to save myself some writing, all they did to go from this step to the next one, they moved this to the front. That's all they did. Okay, so I'm going to do that in blue. So I'm going to put this out front, minus 1/2 delta x f of x n, and I'll erase it down here. Okay, that's all they did on that step. So they moved it out to the front, so those two are together. So the weird terms they put out front. Okay, so those two terms they put out front, and then they left all those alone. Okay, now let's go to the next step. Let me skip that for a second. Look at this, look at all these terms right here. They all look the same. F of x1 delta x, f of x2 delta x, dot, 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 f of x n delta x, f of x n minus 1 delta x, f of x n delta x. We can write that as in summation notation. So we can write all of that as the sum, I goes to 1, from 1 to n, of f of x I delta x, right? When I is 1, you get f of x1 delta x. When I is 2, you get f of x2 delta x. Keep going. When I is n, you get f of x n delta x. Okay, so that, notice that they've done that. They wrote all that mess as a summation. And now let's rewrite this. So let's factor the 1/2 delta x back out of that. 1/2 delta x, you have f of x naught minus f of x n. Okay, so that's where that came from. So again, so the two weird terms they pulled out front, all of these have the same form, so we can write that in summation notation. And then these two terms, you factor out 1/2 delta x, you get f of x naught minus f of x n. So that is the first part of the next to last line there. Okay. And then if you continue following over the next step, okay, so 1/2 delta x is b minus a over n. No problem. Now remember, x naught was the same as a, our left endpoint, and xn was the b, the very right endpoint. So this is the same as f of a minus f of b. All right? And then we still have this summation here. Okay? So that's we finished the next to last line here. Okay, so I haven't been writing limit. Let me go back down and take the limit of this, and we'll see what we get. So all this is right now, this is still, you know, assuming the curve is above the x-axis, this is still the area of the trapezoids, right? It's just written in a different way. So this is the area of the end trapezoids. Now let me take the limit as n goes to infinity of this whole mess. So I'm just taking the limit of this. So this is exactly what we did when we did rectangles. We chopped the graph into equal intervals. We drew in rectangles. We found the areas of the rectangles. So the sum of the areas of the rectangles was an approximation of the area under the curve, assuming the curve was above the x-axis. And then what we do to get the exact area under the curve, we took the limit as n went to infinity. So that's what we're doing here as well. Now, when n goes to infinity, half is just a half. B and A are constants. B minus A is a constant. F of A is a constant. F of B is a constant. Those are just the y values of the endpoints. There's no n involved with any of those except for here. And notice it's in the denominator. So when n goes to infinity, you're dividing this positive number by a larger and larger and larger number. This term goes to 0. Right? You have a constant, a constant, a constant, a constant, and the denominator is getting huge. So when you take the limit of that piece, you just get 0. So notice this turns out to be just the limit of the last part here. Right? Because that goes to 0. Now let's focus on this. Well, what do we have here? I have the limit of a Riemann sum, right? Riemann sums look like f of some points times delta x. And what's the definition of what do we have? The limit of a Riemann sum, that's the definition of what? A definite integral. So the limit of a Riemann sum is the definite integral from a to b of the function f of x. And there we go, pops right on there. So notice whether you use rectangles and do areas under curves, or you do trapezoids to do areas under curves, when you take the limit as n goes to infinity of those, you get the same thing, definite integral. All right, so this shows you if you do rectangles and let n go to infinity, or trapezoids and let n go to infinity, you approach the area under the curve. Okay, so that was that. So that's the second part of the theorem. Theorem 8.3 says, moreover, as n goes to infinity, the right-hand side approaches this. So when you take the limit of the right-hand side, you do get the definite integral, just like you did with rectangles. Okay, let's do an example. So we proved the formula. We proved that when you take the areas of the trapezoids, if n's large, it'll be a good approximation for the area of the curve. And if you let n go to infinity, you actually get the definite integral. Okay, this number 11 says, let me write this integral, 0 to 1, 2 over x plus 2 squared dx. The instructions say, use the trapezoidal rule to approximate the definite integral. They don't want you to work out the definite integral, they just say approximate it with the trapezoidal rule using 4 trapezoids. So n is 4 here, 4 trapezoids. Round your answer to 4 decimal places, okay. Okay, so if we use trapezoidal rule, what do we need to do? I don't need to draw a picture of this function. Notice from 0 to 1, I mean, because this is a square, this curve is on or above the x-axis. So the actual definite integral is the area under the curve. Right, so let me just imagine the integral from 0 to 1. Well, what's delta x here? It's b minus a, 1 minus 0 over n. Oops. N is 4. And so you get a 4. So delta x is a fourth. So we're going to chop this up into 4 pieces. Well, this is clearly going to be a fourth, a half, and 3/4, right? Delta x is a fourth, a fourth, a fourth, a fourth. So these are the x values. So this is x0, x1, x2, x3, x4. Right? I don't need the graph or anything. I just need to figure out how to chop up the interval. Okay? So according to the trapezoidal rule, this integral is approximately, now remember what the formula says, it's b minus, it's 1 over n times, it's half delta x, or b minus a over 2n. Okay? So it's b minus a, 1 minus 0, over 2n, times, now remember the generic formula for trapezoidal rule says you take f of that one, the left endpoint, 0, f of the b, f of 1, and 2 times f of all the ones in between. Okay? So I need f of 0 plus 2 times f of a fourth plus 2 times f of a half plus 2 times f of 3/4 plus f of 1. Okay? So that's the trapezoidal rule. Remember, it's b minus a over 2n, f of a, f of b, 2 times f of all the ones in between. So those three. Okay, so if we continue, that's 1/8 times. Now, just to save some time, I'll tell you what these turn out to be. So again, this is the function f. When you plug 0 into there, you get a half, plus 2 times. When you plug a fourth into that, into the function, you get 32 over 81. That's a fourth. When you plug in a half, you get 8 over 25. When you plug in 3/4, you get 32 over 121. And f of 1 is 2/9.